Day 2 of 365 stayed on the performance theme, but with a more practical target than day 1. Yesterday gave me the language of Big O. Today was about learning the common time complexity classes well enough that I can look at code and make a fast judgment about how it scales. That matters because most algorithm mistakes are not syntax mistakes. They are growth mistakes, and time complexity is the tool that makes those mistakes visible early. The first big lesson was that time complexity is really about the shape of work as input grows. O, 1, O, n, O, log n, O, n log n, and O, n squared are different growth shapes, not just labels in a chart. Once that clicked, the topic stopped feeling abstract. The real question became, what does this code structure imply about growth if the input gets much larger than the tiny examples I used while writing the solution? The second useful shift was recognizing constant time and linear time quickly. O, 1, means the amount of work does not grow with input size. Array indexing is the classic example. O, n, means the work grows in direct proportion to the input. A full scan through an array is the cleanest example. That is not automatically bad. In a lot of problems, linear time is already the best possible answer because the algorithm has to inspect each element once. Another big lesson was connecting logarithmic time to repeated halving. Binary search is the usual example because every comparison cuts the remaining search space in half. That growth feels very different from a linear scan, especially once the input gets large. It is a reminder that the structure of the algorithm matters more than how short the code looks. A slightly more thoughtful structure can change the growth class dramatically. That also made O, n log n, easier to understand. Efficient comparison sorting often lands there because the algorithm does logarithmic splitting or organization while still touching all n elements in a meaningful way. Merge sort is the standard example. It is not magic. It just avoids the explosive growth of repeated pairwise comparison patterns that show up in slower quadratic approaches. The most practical lesson today was that O, n squared, is the first serious warning sign. A nested loop over the same input is not always wrong, but it should make me pause. If I see it, I want to ask whether hashing, sorting, prefix sums, two-pointers, or a different data structure could reduce the growth. That is where runtime intuition starts becoming useful. Time complexity is not just a label after the code is finished. It is a reason to search for a better approach before the code is finished. Another useful shift was focusing on the dominant operation instead of getting lost in tiny details. Two separate linear loops are still O, n. A big constant does not usually change the complexity class. The part of the algorithm that grows fastest is what matters most. That is why nested loops, repeated scans, and avoidable sorts deserve attention. The goal is not to obsess over every instruction. It is to identify what actually dominates the work. This also matters outside interviews. A production system can slow down because a hot path is doing more work per request than expected. Maybe a lookup stayed linear when it should have been indexed. Maybe a feature introduced a nested scan on growing data. Maybe a sort is running too often in a latency-sensitive path. Time complexity is one of the simplest ways to notice those risks before they become operational pain. Another thing Day 2 clarified was that runtime classes become much easier to remember once they are tied to code structure. Constant work, full scan, having search space, divide and conquer, nested comparisons. Those patterns are much more memorable than raw notation. That is the mental model I want going forward, because later topics like binary search, heaps, and graph traversal will make more sense when the performance shape is already familiar. So my main takeaway from Day 2 was that time complexity should become a code reading habit. Ask what operation dominates. Ask whether the algorithm scans, halves, sorts, or nests work. Ask whether quadratic growth is really necessary. If those questions become automatic, future DSA problems become easier to evaluate and improve. That is what made today useful. Runtime classes stopped being vocabulary and started becoming judgment.